Yeah, and so good afternoon, everyone, and welcome to our seminar. I'm your today's host from the UQ SFP Students Chapter. A quick note, please keep your mic muted during the presentation. We will have Q&A section at the end, and feel free to drop your question in the chat. So we're honored to have Dr. Anthony Chen Yan with us today, with a decade of experience in computational fluid dynamics and fire simulation. Dr. Yan is associate professor at Hong Kong Polytechnic University and adjunct lecturer at the University New South Wales. Today, he will sharing a atomistic modeling approach for fire retardant materials and coupling with CFD. Without further ado, let's welcome Dr. Yan.
Well, thank you very much for the detailed introduction. Thank you, Jioru. Anyway, let me quickly share my screen. Luckily, we just tested this right now, so I guess it should be fine. Let me know if there's any issues. So I will just quickly. So is the whole screen pop up? Okay,
yeah.
Thank you. Thank you for the confirmation. Today's presentation is about atomistic modeling approach for fire retardant materials and how it couples with the CFD framework. So before I talk about that, let me just quickly introduce myself. I'm from the Hong Kong Polytechnic University. I'm an assistant professor, not an associate professor yet. I'm also a presidential young scholar. I would like to give credit also to my colleague, Dr. Timothy Chen, from also an assistant professor from CTU. We've been working together for more than 10 years. And our PhD student, Ivan Cordero from UNSW, and Enzo Chen. So notice I got students from UNSW because just a year ago, I was still working at UNSW. And I since graduate and then working as a postdoc, I've been there for more than 11 years. And I want to give some tribute to my previous supervisor and mentor, Professor Guan Heng Yo. I got his book here still. So we've been starting working on CFD, eventually migrate a bit to molecular dynamics. So today we would like to share some of our past experience with regards to our research in fire retardants. So to begin with, I would just like to quickly share you the outline and some of the framework that we have created for our research. So obviously we got to talk about some of our case study we encountered before in New South Wales. And then we will talk about the molecular dynamics theory and how it is suitable for targeting some part of the problem, and how we can use this effectively to characterize the so-called flame retardant mechanism. And there are some case study we can look into different types of fire coating material, and more importantly is how we can link this information we extracted from MD into our CFD models for more precise description of the material that we are dealing with, say like any polymer composite, aluminium cladding panels, and so forth, and some future works that we've been looking forward to. So let's start with our research motivation. So Guan and I, a long time ago in 2011, 2012, sorry, I should say Professor Yo from UNSW. He's a CFD expert, and we together, since I joined PhD, we start looking into fire safety problems. And our first big case study is actually, unfortunately, because of a tragedy happened in the aged care facility at the Quakers Hill, New South Wales in 2011. So the Fire Rescue New South Wales come to us asking about an investigation study, but they are not sure where the fire origin started. They just have footage about the fire scene, as you can see on the right-hand side. This fire is actually there's 4 beds, hospital beds within the room, and they they were gathering evidence to convict a victim, which eventually he's being caught. And this piece of experimental and numerical work was given as a court evidence to convict the victim. I believe his name is Roger Dean. And in this case study, we are looking in to many materials burning, involving mainly polyurethane. But I guess the most important thing is to get the fire scene correctly. But we struggle a bit in getting the actual fire scene. But eventually we find that the window breakage might be the most important factor for this case scenarios itself. So looking at the configuration of the room, there's thermocouple trees putting on the circled region. We have L, B, R, and F describing the location of the couples. And then what in the experiment we do is just to gather validation data. And of course, we use the simulation to try to replicate the fire scene so that we can learn which is the actual fire scenario that matches with the fire debris at the end of the day. So we tested on bed number 1, 2, 3, 4. It doesn't match exactly, but what we find eventually is I think the suspect actually burned 2 beds at the same time, which is bed 1 and bed 4. I think that at the end of the day matches the fire scene. So we believe that is what actually happened. So 2 beds were lit simultaneously, and then eventually this fire went to flashover and burns rigorously. But another fact is actually in the fire scenario, most of the occupant escape, but after a while, because the inhalation of smoke, I think a few of them pass away after they manage to escape the room. So fire and toxicity is also a big consideration in this case scenario. And unfortunately, we cannot look into that in detail in, say, fire dynamics simulator, but we will talk about the more detail about toxicity prediction in the upcoming slides. But basically, here are some prescribed material libraries that I initially got on the web to insert in the FDS framework. So we have yellow pine involved for the drawers and wardrobe. Moisture is because we consider the chairs are with moisture content, maybe 0 to 5%. We have fabric, we have polyurethane foam, and polyurethane is quite standard in FDS, so you can find that easily. Some part of the materials I extracted online, and so for most of the soft furnishing, it's covered by a bit of percentage of fabric and mainly foam, 98% to 2% to be precise. So after we construct the fire model, here is what it looks like. So basically, as I said, like we find that the fire actually starts at 2 beds instead of just 1. And at the beginning stage, the pre-flashover stage, the fire just grow locally on the 2 beds, and eventually it spreads to the drawers and the chair. But at this stage, there's no flashover involved. But what's interesting is the next scene. Like within a short period of time, when this window breaks, all of a sudden, the fire is, because of the entrainment on the left, dragging the flow from left to right, causing a rapid heat transfer process due to the convection effect, causing the whole room to be caught up on fire at a very short period of time. And we believe that is the cause of the flashover. And we can see more detailedly in the HRR curve in the next slide. But before that, like the fire will slowly engulf all the materials within the room, and the fire site slowly decays when the materials are all burned out. And at the end of the fire scene, there's some leftovers, and we find that at the end of the day, it matches the experiment well for the fire scene. So looking at the heat release rate curve, you can see that the most drastic change occurs between the window breakage period, where you have a jump in your heat release rate all of a sudden to around 12 megawatts. And as fire engineers, we are fully aware these are the typical stage you will encounter in a typical compartment fire with furnished materials. And the quality is not that high. But anyway, so even comparing the temperatures, it's doing not bad. Like for FDS, there's a bit of underestimation for some of the result, which is always not good. We want to overestimate a bit to be more conservative. But I think the main limitation is, like I said, we cannot predict the toxicity generation. For example, the carbon monoxide, the hydrogen cyanide, the NOx product. I think these are the main issue that makes us want to look into detail of how we can fully characterize these toxicity, because we know inhalation of smoke and toxicity is a major killer in the fire scenario. So it also lacks a detailed description of the soot formation process. So hence it cannot give us like the variation of soot particle size, so it's also difficult for us to have a detailed description about the concentration of the smoke without knowing these details. And not to mention, it cannot put in consideration the flame retardants within the simulation process. So in the experimental method, typically, the way we characterize a material is through some benchtop equipments. For example, you have your thermal gravimetric analysis tests to get the mass loss rate of the material. And I believe that these equipments are all available in UQ. So it's a researcher's dream, especially for fire safety researcher, to have all these always available at your hand. Because with these, you can always get the most fundamental information of thermal degradation for your materials, whether it's flame retardant or non-flame retardant. And another thing that is important is the cone calorimeter, and I don't think it needs any introduction. It gives you the flammability limits of the material that you're testing. But sometimes on top of that, if you couple it with the Fourier transform infrared spectrum, it gives you the gas decomposition data as well. So we can somewhat look into the toxicity, but again, those are just a spectrum result. It cannot give us the exact amount of concentration of the species. So here I would like to introduce you the molecular dynamics approach. So the reason we look into this is because we know that, especially for solid combustibles, if we look at this figure alone, sometimes it may burn and then involve two phases. Sometimes it has a molten phase if it's like a thermoplastic material. And majority of the cases from solid to gas. So say, for example, if we're burning a wood, so very high chance it would just directly burn to gas phase. But the problem being is how can we actually identify what is the gas volatiles, and out of the gas volatile, how combustible they are, because pyrolysis and combustion are two processes, but they are very closely linked to each other. So it is very important for us to have a way to identify clearly, if I burn this material A, what kind of chemical components it will give me. And I guess molecular dynamics in that regard, if we know the composition of the material at the solid phase, we can roughly estimate the gas phase materials there. Not only that, we would like to look into some specific flame retardant mechanism. For example, the obvious one is the char formation. So some materials, when it's involved mainly like carbon-based chain, these have a high likelihood to form char. So the problem again being is typically we just look at the TGA and then we look into the residue, and we arguably say that everything remains are char formation. But is that really true? There's no direct answer to it. But again, if we go to the molecular dynamics and look into it in detail, maybe it can give us some more insight. So essentially what we started to look at in MD is just to look at very generic polymers. So I'm aware that these stuff may be too in-depth. So I just want to go through the basic concept of what we are doing. So we started off with looking into polyethylene, PMMA. So what we aim to do is to extract the so-called the kinetics data, typically replicating the TGA experiment, so that we want to see whether the two curve or the reaction rates match each other from a validation point of view. But before that, we need to understand what the theory of MD is. But what we find conveniently, it is very similar to our concept in, say, particle modeling and the discrete phase models, where you are tracing a particle movement. So basically, it revolves around the Newton's second law, F equals ma. But the difference is we are looking into atomistic forces, like you have your electrostatic, when the Waals, the torsion, the bond, and all those attraction forces due to the bonds and the chemistry. But in detail, on the right hand side, there's more detail about all the force that is considered in the MD itself. But the idea is we summate all the force together, and then we iteratively model the movement of the molecules. So here's how we construct the polymer itself. So we start with, say, any generic monomer chain, and these data are normally available online, so we can easily extract. So say if we are dealing with this polymer here, we populate and duplicate into a linear polymer chain with multiple monomers, and then we just compress this long chain into a very nice cubic shape of a amorphous system. So this is kind of a replica of a nailing process of your typical foam fabrication approach. So here we tested 3 different polymers. Again, they're very generic, but for validation purpose, and this is published in the journal below. And we have high density polyethylene, PMMA, and polystyrene itself. So roughly it looks like that. But one thing I want to address here is the density. We need to always get the density right to ensure our simulation is good. So after we construct the material, we're interested in the thermal degradation. But the way we do it in MD is a more of an accelerated heat up process. So notice that we use elevated temperatures such as 2,800, 3,200, and so forth. And we are talking about picoseconds because MD actually take quite a while to run. So 250 picosecond is 10 to the minus 12. In MD, each iteration is even 10 to the minus 15 seconds. So even one running 1 nanosecond would easily take you a few weeks to complete the simulation for the perspective. And as I mentioned, we model the thermal breakdown of the molecule. So it roughly looks like that. It starts off with a perfect cube. And then once you exert heat onto the surface of the foam, it starts to break. And then when it breaks, we can start to look into the detailed spectrum of each of the molecular breakdown process of these polymers, And what I want to drag your attention is the hydrocarbon formation, because once we identify the key hydrocarbons such as methane, propane, and so forth, we can start looking at the flammability limits in detail. But in this case study, because it's more of a validation case study, we want to get something like a TGA response, more precisely the DTG curve. So we did 5 different cases, and then we do a linear plot to get the slope so that we can identify the reaction rates. So basically, we find that for more simple molecule composition like polyethylene, which is essentially a polymer chain of C2H4, we can get it very precisely because the reaction force field for C and H are pretty good in MD. On the other hand, if it's involving more different chemical elements, it becomes more complex, then there will be a bit more deviation. But polystyrene, you can capture it pretty well as well, mainly because the carbon, the C and H reaction force field is pretty well done in MD. So after that, we look into another very commonly used flame retardant coating, which is the epoxy resin. And the application, so sometimes they apply for the seamless floor and even coating on wood because it has the adhesion function in it. So once you create this epoxy resin, you can easily apply by just a rolling paint type of way. So that's why epoxy is quite popular to embed with flame retardant to formulate a flame retardant applications. So here's a typical example. We're using the most generic epoxy system available. And in this case study, we flame retard the epoxy using some carbonized peanut shell. But in brief, I think the peanut shell, if you carbonize it, that will remain with some so-called activated carbon added with the intumescent coating formula, melamine and phytic acid, will formulate a nice mixture of flame retardants. So what I want to say here is we can actually formulate a combination of material formulation that we do in the real life in MD conveniently. Once we know what additives we add into the polymer matrix. So here are some of the results we can identify as the so-called flame retardant mechanism. And again, the details are published online in this paper itself. So again, when we look into the pyrolysis product distribution of epoxy, we can identify different polymer hydrocarbon molecules, and we can identify even to some extent based on the FTIR how much amount of CO and CO2 are formated in these material. And if you benchmark with the carbonized peanut shell, we will find that there's more response on the aromatics. And eventually, if we look into these details in, say, water droplet formation, we find that if we include the flame retardant, not only it reduces the CO production, but mainly it increased the water vapor formation. And having water vapor in the volatiles is always a good thing, because not only it lowers the heat, it reduces the other incomplete combustion products as well. So I think that's something we prove in the sense of molecular dynamics. But what I want to say here is MD is not an approach that can solve everything. You will find that in most of our work, we combine it with some form of experiment as well. So normally what we do is we create this material and we find something we cannot understand or realize. Then we use MD to aid our analysis on that material itself. So that's normally the drill. So looking at the residue, we can look more clearly how is the role of this activated carbon works in the polymer matrix system, you know. So if you benchmark the two breakdown process, so not only the flame retardant plays a role in protecting the polymer itself. At the end of the day, the activated carbon will formate will contribute a lot to the char formation. So here is another intuitive method to look into char layer formation. So what we do here is using LAMPS, another MD software, but with more user control functions. So what we do is every, say 10 picosecond, we remove the decomposed compounds away from the computational domain. And then over time, the linked chain will remain. And what we find that at the end of the day, there's a pretty nice layer of char remain after the breakdown due to the activated carbon. So this method is proposed by another group. They call it MoSync. So this is one way of characterizing the char content in a more quantitative way. And after that, we look into something more common as a flame retardant, which is the intumescent coating system. And we are about to publish this work itself. So the intumescent, maybe need some description on that. So the good thing about this is not only it chars, the char expands, and when the char layer expands, it formates it changes from a thin layer to a thicker layer, so it protects the inner substrate. And not only that, we will identify more mechanisms such as show forth. So not only we have char, the char itself acts as a physical protective layer to protect the substrate from burning, and it dilutes the pyrolysis and combustion process because it generates, say, water vapor. Not only that, it has the radical or the scavenging effect due to the reduction in gas phase combustion. So we're going to showcase how we can model this in MD to prove this effect exists in the intumescent coating. So let's just look at the neat polymer itself of the burning. You can see there's a significant amount of C2H4, CH4, C3H6, and these are all not good because they are all flammable, especially exposing into high temperature. But if you compare it to the ones that we're adding a flame retardant coating onto the surface, you can see there's a significant reduction because of the formation of H2O or even CO or CH2O and so forth. So this is the so-called dilution effect. But if you look into this case alone, the powerful thing about MD is we can even identify the so-called chemical pathway of the products. So let's, for argument's sake, specifically look at all the phosphorus-based reactions. So we can see not only the that it will form phosphorus because of the phytic acid content. The phosphorus itself is a recirculating reaction. So for example, PO4 will go to P2O7 and then it will go back to PO3, and it's a repeating process. So it slows down because phosphorus itself is quite inert to heat. So it's a good flame retardant effect when you start forming these phosphorus compounds. But the only downside is some of the phosphorus compound may be subjective to toxicity. But not only that, we can find that the pathway for forming water vapor as well. So the water vapor in the flame retardant mechanism is treated as a blowing agent. Not only it reduces heat in the flaming process, it reduces heat because just formating this water H2O itself will dilute the reaction of heat generation. So this is more of the perspective of all the phosphorus base reaction. So it keeps on changing from PO2, and then it's going back and forth. So it has a circulation of the so-called flame inhibition effect. So it reduces the heat significantly. So if you compare apple to apple together between a neat high density polyethylene against a flame retardant one with the intermittent coating, you can see that the number of hydrocarbon molecules is significantly reduced, almost like 1/2. And the flammability reduction may be even more than that. So here's another work that we look into in the more recent days, which is but no longer looking at this today because Maxine has been published here and there for a few years up to now. But basically, we were one of the first group of people to look into Maxine as a flame retardant. So the Maxine nanosheet itself is a two-dimensional titanium carbide material. So the way to create this material is to do chemical etching to etch out the aluminium layer from the TiAlC2 sheet layer itself. So, but this unique structure is very good because it has a high aspect ratio, but a very thin layer. So it is very, very ultra light. And if you add it to, say, a fire protective gear, it won't increase the weight. So it won't increase a lot of the burden. So say if we put it into our fire equipment. But here specifically is what it's looked like if we look into microscopic images. You can see it's like a sheet like flake-like of form. And if you look at the thickness, it's almost like 1 to 2 nanometers. And here are some perspective of the reduction of heat. So, but the thing is how we coat this material onto, say, polyurethane. And this can be conveniently done by using the beauty of covalent bonding. So first, we activate the polyurethane using some acidic solution, for example, PAA. Once we activate it, there's a minus effect on the surface of the foam. Then you put it into a positive solution. Then by the attraction force itself, it is glued together. And then we then put it into Maxine. And then we repeat the process itself until we feel that there's enough layer by layer coating. Then we can formulate a nice polymer matrix with the flame retardant itself. So here we tested a few bilayers samples, like we have the neat sample, we have the ones with 2 bilayer, and you can see if we put more layers onto the foam, it becomes darker and darker. And if we look into the microscopic image again, we can find that identified there's actually titanium content exists and coated quite dispersely on the surface of the foam. That's when we identify the coating is done pretty well. So here are some of the results of the cone calorimeter. So we can see that adding 5 bilayers is already sufficient for a very nice heat and smoke reduction. But I guess adding 8 bilayers obviously will be the most significant result. But to put it into figure, like the 8 bilayer coated polyurethane, we reach a magnificent 60% total heat reduction and 70% total smoke reduction. And the heat reduction, I think there's other variations of flame retardant that can do with that. But I think the smoke reduction is pretty impressive for this this product itself, I think. But overall, for all of the categories, we reach at least 60% reduction. So that's pretty encouraging. And we can immediately tell by the residue of the cone sample is because of the char formation. And you can see it's very defined char as well. And you can see it increases as we included more bilayers. And if we benchmark our work with other layer by layer coatings, we can find that not only we have on the fewer weight gain side, but we have the most reduction in heat and smoke. But more importantly, we want to understand the mechanism, because experiment can only tell us that far. So we look into the molecular dynamics. And believe in me, creating this is not easy as you think it is. I think the difficulty in creating like a nano sheet like that is you have to get the angle and the orientation and the distance between the molecule right and stabilize. So just getting this nano sheet stabilized in the MD is a lot of effort in optimizing the so-called the reaction force field. So in precise, the bonding force between the molecules has to be optimized, and it can be done in the embedded functions in MD using some AI techniques revolving around density functional theory. So basically, in the MD itself, we identify the Maxine has a two-way flame retardant mechanism. So the char content is because of this reaction. It formulates this carbonation compound, the 2C, and TiO2 itself is a good flame retardant material. So once it reacts with heat, it will formulate a two-step flame retardant mechanism that maybe explains why it is so good as a flame retardant. So if we look into the radial distribution function, it confirms our the bonding and the reduce in CC bond distance from the ring structure, and it further confirms more of the hypothesis. So as I mentioned, the most difficult thing is to get the force field to be correct in MD, and this is just an example of how we are actually doing this. So we have to optimize the bonding one by one by knowing each of the components. So say, for example, we have the Ti3C2. So if we want to get the density functional theory to match with our force field, we need to do a benchmark. And for more detail, like the Ti3C2O2, then we need to do it again, one by one. And this, if we purchase the software for MD, is actually quite automatic, but it just takes a lot of time to do. After that is generating the chitosan, because our solution is not only with Maxine, there's actually a bilayer. So it's actually one layer of Maxine, one layer of chitosan, and so forth. And we just populate the two together to study what is the so-called synergistic effect for these two material. So here's what we find, So Obviously, we formulate the carbonaceous compound for the char layer, and the titanium oxide for the further reduction of the fire. And you can see literally almost little to none hydrocarbon is formed during this process with the unique combination of MXene and chitosan. So if we look at a more animation point of view, you can see that the MXene layer still breaks, but in between the layers, it doesn't totally deassociate. I think again, using the hissing method, we can see the remaining coating substrate within the matrix, and we find that it is pretty stable against a high temperature of heat. But what more importantly is that how we link this MD information ultimately to our CFD model. And here I would like to demonstrate you this example involving the graphene oxide. So I believe time is a constraint, so I will go through this very quickly. So this case study alone, we look into polyethylene and polyethylene with graphite oxide. And we know that the TGA response is roughly, if you add graphite in it, obviously it will have a very large reduction in mass loss rate. So we are getting that in the MD as well. And the extraction of the kinetics actually revolves a genetic algorithm we write this code to quickly extract the data to match with our TGA curve. So in short, we have the comparison between free TGA response without flame retardant and with flame retardant. So you can see using this genetic algorithm automatically, we can match the data, say for example, the TGA result with and convert it into theoretical reaction rates. And once we use that, we can utilize this technique for both MD or TGA data, and we can extract useful information for CFD modeling to describe the pyrolysis process. But MD gives us an additional result on the gas volatile, so we can even identify the primary gas that is flammable in the combustion process, which is very important. If you look at this burning of any generic solid combustible, so now we can look into the char layer, we can look into the gas volatile that contributes to the combustion process, and the CFD will deal with the rest involving the radiation, convection, and so forth. So the pyrolysis model is very simple. Like we have the heat exerted onto the surface of a 1D conduction equation. So this is your typical CFD framework where you have your time-dependent term, your advection term, and so forth. But your QNet, besides of the radiation and convection, the combustion contribution can be correlate back to the data we extracted from MD or TGA, which is based on the Arrhenius formation. But more importantly, to make good use of the extracted information from MD in the CFD, we can conveniently use the detailed kinetics model. Say, for example, the GRIMAC 3.0 involving 325 reactions and 42 chemical species. So now we can really deep down look into the toxicity formation, because if we consider the detailed chemistry, we can look into even like HCN, the NOx product, and so forth. And here is just some example of what the detailed chemistry can do. And not only benefits the toxicity prediction, now we can really look into the detailed formation process of soot. So if we use any two equation models, we can look into all the process that revolves around the changing the variation in soot particle size. So not only we look at one specific size of the soot product, we can know the whole spectrum. So because we identify the nucleation, the coagulation, the surface growth and oxidation, so forth. So here are some representation of the CFD result that we produce, and the details can be referred to the publication below. If we benchmark the polyethylene, notice we always do polyethylene because polyethylene is the most easiest and precise and accurate result that we can generate in MD. So we always benchmark it with polyethylene to begin with. But we are working on polyurethane because we know that polyurethane is more commonly used in soft furnishing in our beds, in our sofas. So, but polyethylene is also very commonly found, like including in your ACPs and so forth. So I think it's also important. But anyway, we find that the polyethylene will burn out quicker. So you say you can see at 180 seconds it's almost totally burned away. Whereas if you put flame retardant into it, not only the fire is smaller, it takes longer to burn as well. And the heat release rate curve somewhat agrees with our finding, comparing the one with GO and without GO. And of course, you have a lot of heat reduction if we put graphite into the matrix, roughly around 24.4%. But more importantly, we can really look at the layer thickness of the char in the CFD at different times, you know. So if we compare the two together, you can see little to no char is formed if we just burn a pure polyethylene. But if we put the graphite oxide into it, you can see a nice thick char layer is formed, and we can somewhat measure the thickness of this char layer. And combining the MD with CFD, that's the good thing about it. And we can look into detail the concentration of different chemical compounds such as CO2 and CO. We can actually look into more, but due to time constraint, I didn't plot the data for this information here. So in short conclusion, for this presentation, we created some flame retardant materials, and mainly the most significant one being the 2D nanosheet material, Maxine. And what we find that if we cannot identify the in-depth flame retardant mechanism, we can use molecular dynamic simulation to aid our understanding from the atomistic point of view, and we can identify the interfacial science such as oxidation and the thermal degradation effects, and we can really look into the molecular breakdown of the bonds and the decomposition kinetics of the chemical compounds. And this information, more importantly, can be fed into our CFD models for better prediction of toxicity and soot formation. So I hope this presentation gives you guys some insights on numerical modeling in fire, and I hope you enjoy it. Thank you very much. And here are my contacts.
Thanks very much, Dr. Anthony. I'm personally, I really like the presentation. I'm not a fire dynamic research, but I feel like it's really easy to follow, and I really like the idea to look like at really microscope levels. Thanks for your presentation. And is there any question from the audience? You can feel free to unmute yourself now, or you just type in the chat box. I thought Debbie is speaking, or we cannot like receive your voice, but I saw like you unmute yourself, and looks like you are speaking, but we didn't get your question. I just got a question about recording. Yes, we will upload the record to our YouTube channels. We got the SFP, UK SFP chapter on the YouTube. Just got two questions about recordings. Yeah, we will upload on YouTube channel, UK SFP. We got two questions from Wenxuan. He shared his question in the chatting box. Did you? I mean, Dr. Anthony, did you
Oh,
say
sorry,
the
sorry, sorry.
question?
I thought you're gonna mention it. But anyway, where can I find it?
The chat box,
Okay.
the chat.
Chat.
Yeah.
Let me see. Sorry, I'm not very familiar with Zoom, so I'll just find a way to look into it. Yep. It's recorded. Yep. So oh, thank you, Weng Shuan Wu, I believe. So TJ coupling with IR can actually give the concentration other than the spectra by conversion quantification process. But GCMS, TGMS might be better option. Have you considered the validation of MD simulation by doing those? That's a very good question. Thank you very much. Um, Yes, I do. But when I was in UNSW, I guess next to my office is the fire lab only with TJ and IR. Of course, we want to do GCMS, and I believe it is a great idea, but by having the equipment available. But I know the limitation for GC and MS as well. It has to be calibrated to the correct setting to target for a specific flame retardant combination we look at. So I think we just need to be mindful of that. But otherwise, it is a perfect match with the MD validation itself. It is a better option. You're right. Oh, and another thing is just want to send my regards to all my colleagues in Queensland. I see a lot of familiar names on the chat, so just want to say hello and hope you're all doing well. The second question is to be able to use MD simulation, how deep we should go into chemistry level for the material. I think in my personal opinion, I started as a physicist and a mathematician, I guess more precisely. But I guess when I was looking into MD, it does take a lot of understanding for the chemistry part. So I would say 80% understanding is chemistry. So you do need quite intense study into the polymers and the look into papers to even understand what are people hypotheses on the reactions itself. Because without this understanding, you don't know what you are looking for, if that makes sense. Anyway, I guess we have one more follow-up questions. Or say the competence level to use MD simulation. As I noticed, you even need to take care of the angle of the molecular, how sensitive it would be if I made minor mistake imperfection. I would say this one is more straightforward because if you don't get it right, immediately the thing will break even without adding any heat into the molecule, you know. So it's quite of a, how to say, straightforward to see whether your modeling is working or not in MD. Because if you don't get it correctly for your force field, it doesn't work at the get-go.
Thanks, Dr. Anthony. Thanks, Wenxuan. Really good question. And is there any further question or more question from other audience?
Hi, Anthony.
Hi, Venkata. How are you?
Good to hear from you.
Yeah.
I just had a question regarding your the modeling steps. So on one of the slides, you show that you have to achieve a particular density of the polymers. Just wondering how you achieve that. Is it a specified
Oh,
number of chain lengths or some other technique?
oh, it's very abstract. Actually, we do an Excel calculation on the molecular weights of these compounds that we add into the system, and we know roughly the volume where we define it in the MD, and we just calculate the density straight away based on the Excel calculation. Yeah.
So it's basically empirical. So you just add all the molecular
Yeah.
weights and then weight over
Yes.
volume, I guess.
Yep.
Okay.
But
Thanks.
in the simulation, it would give you a theoretical rate as well. As long as that doesn't deviate too much, then you are on the right track.
Okay. All right.
Do we still have more questions on the
Yeah, I mean,
chat?
if you get a question, like, just feel free to send your message or just directly unmute yourself.
Yeah. Very happy to answer anything. I think as we would like to promote our techniques to engage more researchers to work on MD with us as well. I think that's that. So I guess that's about it.
Yeah. Seems like it's well presented, and yeah.
Wait.
We got Wenxuan's third question.
Yeah, oh, really appreciate this, Wenxuan. So a question regarding the flame retardant. Since you could not find out the toxic gas concentration as a correlation with the fire retardant concentration, will you propose an optimized concentration, as this is good proof that fire retardant is not a silver bullet to everything? Sorry, I don't have mic, otherwise it would be. Okay, that's more of a practical consideration about the flame retardant content. So one good example we just did now is the Maxine. The reason why we need to look into lighter material is because we find that, say, polyurethane foam, because originally it is quite light to begin with. If you add a lot of flame retardant into it, it will become very stiff and rigid, and it is no longer comfortable for you to sit on, you know. So I guess the right combination not only comes when you don't just look into the flame retardant properties, you also need to be mindful of the mechanical properties as well. So really based on the application of your polymers, you know. If you want to work on soft furnishing, then you can't add too many flame retardant contents. So I think it's more of other concern due to the multifunctional properties of the materials that we are solving. Yeah. So another example is like if we're looking at a sound absorption material, maybe we can allow us to put more flame retardant content into it, but we still need to be looking into the sound absorption property as the main, you know. So I think hopefully that answers the question.
Thanks, Wenxuan. Thanks, Dr. Anthony. Right, Wenxuan says thanks very much. Very nice presentation. He
We
definitely
can
have
talk offline,
look at
Wenxuan.
the simulation later.
Yeah.
Yeah. I actually have one question. It's like so you diving into the MD simulation and you get some results. I mean, how those results going to affect the safety model and eventually affect to the fire safety engineering strategy, or even a fire structure, fire resistant design? I mean, how big impact will it give us different conclusion? That's my question from my own aspect.
Well, that's a very, very good question as well. I think the impact at the moment is not very massive, because we haven't created a full material library for even say as simple as polyethylene, because not only polyethylene comes in different form, different density, different range, it has high density as low density. So I think we take time to generate enough data for us to be making it useful in say FDS or whatever. But I think immediate impact is the toxicity prediction, because previously we weren't able to do that even in our CFD model. Because my PhD thesis was working on toxicity, and that's where I find I struggle in identifying the toxicity of different materials, because there's literally no way of doing it until we discover this MD technique where we can look into the whole spectrum of the chemical compounds that can come up from that specific combination of the polymer. I think there's no way other than that to look into, no quantitative way to look into that at the moment.
Yeah, but it potentially could at least maybe change the evacuate time, like change the
for the prediction of the A set and R set. I guess for that regard, I think it's more important to get the smoke formation right. But at the moment, I won't say it makes a super large difference, because I can't just lie about it. Because at the moment the smoke prediction is not too bad. As long we get roughly say polyurethane will give you a certain amount of soot yield. It won't be too far off, even you use a more precise model. But looking into the smoke particulates itself, we can look at the size of the sooty particles. So maybe it can tell us more about the sootiness of the flame.
All right. Yeah. Right. Got it. Is there any last minute question from the audience? Otherwise, we're going to it's time to end today's seminars. All right. I think that's all we got. We got really a lot of really good questions from the audience as well. Thanks to attending today's SFP UK SFP student chapters seminar. As we said, we will upload the recording to our YouTube channels. And once again, thanks Dr. Anthony to give such a nice presentation. Thanks for your time. And I see you guys next time.
Thank you for having me. Have a good day, everyone. Bye-bye.
Bye.